Hi, I'm Jana. I'm going to present our LIX 2019 paper, The Hierarchy of Hyperlogics. So let's jump right into things. This paper is an expressiveness study of how temporal hyperlogics versus first order and second order hyperlogics compare. So this work was inspired by Camp's famous theorem, which states that linear temporal logic is expressively equivalent to first order monadic logic of order. There are also similar results for other prominent logics like QPTL, S1S, QCTL, QCTL star. And basically, to summarize our result, temporal hyperlogics are less expressive than first order or second order hyperlogics. And this gives us a real hierarchy of logics. Okay, so let's take a step back. What are hyperproperties? So in short, hyperproperties relate multiple execution traces. So if you take the view of the system as being represented by a set of traces, hyperproperties relate these execution traces. The possibly most simplest hyperproperty is stating that all traces must globally agree in A. So you cannot express such a thing in LTL, for example, because you have to compare every trace that is in the system. And so this is why this is a hyperproperty, not a usual trace property. So hyperproperties is quite an abstract concept. There are many properties that are in fact hyperproperties. So for example, non-interference or even distributivity can be formalized as a hyperproperty. And in particular, epistemic properties also. So in epistemic properties, what happens is that we have an agent or several agents that observe the system that is running. And the important thing here is that the agent has only a limited view on the system. So some traces might be or might occur the same for the agent. So for example, here the second or in the third trace might be the same for him. So he cannot know which trace is currently executed. So for example, if he wants to state, okay, I know that at this position, phi holds, we not only have to prove that really phi holds at this position, but also that phi holds on any other trace that is inseparable for the agent. So also on the third trace. So this means that we have to compare all traces that look the same to the agent and prove phi on all these traces. So this is why epistemic properties can be formalized as hyperproperties. There are a bunch of logics for hyperproperties. The most used one are temporal logics. So you can get a temporal hyperlogic by taking a temporal logic and adding trace or path quantification. Most prominently, hyper-LTL is obtained by taking LTL and adding trace quantification. So if you go back to our example, if you want to state that all traces globally agree in A in hyper-LTL, what we do is we universally quantify two traces. So for example, these two, and then in LTL state that globally, if A holds on one trace, it also holds on the other trace. So the inner formula here is just a usual LTL formula where the atomic propositions are indexed. But not only temporal logics exist for hyperproperties, also first order and second order logics. And similarly, we have a way to obtain first order, second order hyperlogics by taking a monadic first order, second order logic, adding the smaller predicate for the time, and for the hyper level, the equal level predicate. So for example, starting from first order monadic logic of order, by adding the equal level predicate, we have a hyperlogic. Similarly, we can also state our property here by taking any 2 points on this kind of grid we have here and say that if they are on the same level, this is the binary predicate, the equal level predicate here, then they also have to agree on the predicate A. So this is quite a classic first order logic we have here. So what we did, as I already mentioned, we compared the expressiveness of these logics. And what we have is that for the linear time logics and also for the branching time logics, these logics are quite different. So in general, the temporal hyperlogic, for example, hyper-LTL here, is strictly less expressive than the corresponding first order logic. Corresponding meaning the logics that have equal expressiveness in the non-hyper level. So we have a real bunch of logics we can choose from. And for example, we could choose hyper-QPTL, which can express the knowledge operator you might know from LTL with the knowledge operator. So we can do real epistemic reasoning in this logic, but while also having possibilities to express all omega regular properties, for example, or also we can encode distributed architectures, allowing us to reason about both things at the same time. Similarly, classic reasoning methods like the Tableau methods, chase methods might now become applicable to hyperlogics by applying them to first order and second order logics. And this might end up in new decidability results even. So yeah, if you're interested, check out paper, The Hierarchy of Hyperlogics. Thanks.